Your next step is to design each network and determine the distribution center components necessary to support them. We'll step you through each of the networks, starting with the voice network.
Now, the voice network simply needs to distribute at least 4 incoming voice lines to the various voice service modular jacks throughout the home.
Each manufacturer of structured cabling products will have some type of voice network distribution module with or without a cross-connect. There are 2 methods used to terminate the TP cable runs to the module. The first terminates the cables in modular connectors. The cables then plug into the voice distribution module like this. The other method terminates each cable in a 110 style insulation displacement connector. The connectors are wired in parallel and connected to the incoming voice lines.
In our project house, we need to support 24 voice outlets. So we'll be using 3 of these 110 style telecom distribution modules connected together.
Secondary overvoltage protection on the incoming voice lines is a good idea, and most manufacturers provide this protection in some form. We'll use this surge protection module wired between the incoming voice lines and the distribution module.
The design of the data network is also straightforward. The goal is to electronically glue everything together so that every network device has access to every other device and the network is connected to the internet.
First, determine the broadband internet access. In our case, we plan on using the cable provider, but we'll be pre-wired to use DSL as well. All current cable or DSL modems have Ethernet ports to connect to a router.
Now, the second step is simply to add up all of the outlets and devices that need access. Now, as we did our walkthrough, we determined the need for 20 data outlets.
We'll also pre-wire network access at thermostat, the security panel, and so on.
Right. Like the voice network, you'll need to determine how the data lines are terminated in the distribution center. Now, we chose to use 3 of these data termination modules. They have jacks on them so you can select which data line is connected to which switch port.
Next, diagram the network to determine what equipment you'll need to support the attached data jacks and devices. Since the router seldom has more than 4 ports on its built-in switch, you'll need to add additional switches. In our case, we needed 2 additional 8-port switches. The heart of our network will be this Ethernet router with a built-in 4-port switch mounted on a snap-in bracket. To support wireless Ethernet devices such as laptop computers, we'll install this wireless access point in the top of the hall closet. And at trim-out, we'll purchase and install the cable modem in the bottom of the enclosure. This camera server takes the input from up to 4 cameras and converts the image to a web page with a pre-assigned URL, so it can be accessed from the in-home data network and from the internet. We'll connect its Ethernet port directly to one of the router switch ports.
Next, we need to design and specify the RF broadband distribution system.
Right. Now, the goal is to combine the external sources with all the in-home generated sources and distribute the combined signal at an adequate signal level at all external outlets.
The first step is to itemize the external source inputs that we need to support. In our case, we plan on using cable service as our primary source with the pre-wired option for off-air digital television. We also plan on supporting satellite, but we'll talk about that later.
Then simply add up all of the external jacks that you need to support and all of the internal jacks to support AV sources. Now, when we did our walkthrough of this project house, we determined we need to support 15 external cable outlets and 12 internal outlets for AV sources, cameras, and so on.
Start with a simple diagram of the system. Now, once you've done one, they're easy to modify for other jobs. First, show all the external service inputs. Then, based on the equipment list and plans, determine the total number of in-home sources and jacks and the total number of external devices and jacks you need to support. All internal coax runs are combined into a single internal source that contains all the modulated channels. Depending on the number of inputs, the combined signal may need to be amplified. The external source is also amplified, and the external and internal signals are combined. The result is then split as necessary to support all the external cable runs. Almost all residential distribution systems will be some variation of this design. Once you have the system diagrammed, you need to determine the source and destination signal level requirements. You can assume that all the receiver input signal level requirements are between 0 and plus 10 dBmV. We use a signal level notation that lists the maximum and minimum signal level that we have or need at each location. Cable company signal levels should be at least plus 3 dBmV at the NID, but you can expect a variation between 0 and plus 10 dBmV. Off-air signals will definitely have the widest range, from minus 10 to plus 30 dBmV. Modulators, including those built into cameras, will typically have outputs in the plus 25 to plus 35 dBmV range. The next step is to calculate the losses through the system and the gains required to overcome the loss. On your system diagram, list the loss through each passive component, such as splitters, filters, and coaxial cable. You can use a rough rule of thumb of minus 5 dB per 100 feet for RG6 cable runs. Then work backwards from the required signal levels at the external outlets, applying the loss through each device to determine the signal level required at each point to overcome the loss until you get to the amplifier outputs. Then work forward from the signal inputs, applying each component's loss until you get to the amplifier inputs. The gain required by the amplifiers is simply the difference between the signal inputs and the required signal at the outputs. This diagram, also in your workbook, shows our initial design and the loss and gain calculations we did to determine the gain of the external and internal signal amplifier. We then converted that into a network design drawing showing each part we would need, as well as the jumper cables between the components and which cables would attach where.
Now you can build a system from individual components such as splitter combiners, amplifiers, filters, and so on, giving you maximum flexibility.
Or you can use distribution modules that combine these components for you.
Now, since our system is a lot more complicated than a typical production home, we're going to be using the individual components you see in the diagram.
We also designed the satellite signal distribution. This operates independently from the rest of the RF distribution system. We chose to provide up to 8 satellite receiver locations by incorporating a multi-switch that operates with a DirecTV 3LNB dish.
Now we'll take you through more of the design details of the system, including the channel plan, in Part 4, when we install and configure the system. 50, yeah.
So let's just get 50.
Next, Rich and I completed our equipment list with all the parts we'll need for the job. We selected the wall plates and jacks and the distribution center network components, including the distributed audio equipment.
Right, so I've got...
We also made a list of the type and quantity of cable we'll need from the totals on the cable schedule. We then worked on determining the size of the enclosure we need to contain all the components. Take the time to determine how much enclosure space you'll need for each network, as well as power supplies and then the room necessary for routing and securing the cable. Then you can select the enclosure height that accommodates everything with some room to spare. To save a lot of trial and error during trim out, we did a layout drawing of all the equipment we'll need for each network. The drawing shows where components will be placed and the length of any jumper cables we'll need, so they can be made in the shop ahead of time. While doing our layout design, we discovered we'll need at least 2 50-inch enclosures for the voice, data, and broadband RF networks, and an additional 26-inch enclosure for the security system and A-bus audio distribution system. Now the first 50-inch enclosure holds the broadband RF components, and the second 50-inch enclosure holds the voice and data network components.
We've got a
We've
pair
got
of speakers.
speakers in the ceiling. Oh, I was going to center them around maybe the... At least
Planning can really make the difference between a smooth, quick installation with no callbacks and one with a lot of wasted time and customer problems. It doesn't take any more time to do it right. Once the planning process becomes a routine part of the job, it will pay you back every job in time and money saved.
We've got the power that we need.
This end is good.